Hi there. The purpose of this video is to give you an overview of the process I might go through in order to create a mathematical engineering problem. The problem presented at the end is definitely not in a finished format in any shape or form, but that's not the purpose of this. The purpose is kind of how I go about trying to find an engineering problem for my students to engage in. So if we look at the requirements for your final project for S109, you're to create an engineering design challenge that's centered on an authentic problem. Within that, you have a couple of options. You can engage your students in a full design challenge, or you can just engage your students through the part where they have to define the problem, and maybe you practice a questioning strategy. It's okay that if you do not have time in your curriculum to do a full design cycle, it would be great if you could, but if you don't, we fully understand that. The purpose of this is for students to work on figuring out how to define an engineering problem. So Friday I posted what an engineer might do with each of those science and engineering practices in hopes of helping you find points of commonality or an entry point in order to help you define your engineering problem for your S109. The whole purpose of this is for students to practice at asking questions and defining problems. So while science begins with questions, engineering begins with defining a problem to solve. However, engineering may also involve asking questions to define a problem, such as what is the need or desire that underlies the problem? What are the criteria for a successful solution? Other questions arise when generating ideas or testing possible solutions, such as what are possible trade-offs, what evidence is necessary to determine which solution is best. So these are the types of things that we want our students to be engaging in within the lesson that you design. While you may look at this and say planning and carrying out investigations is a science practice, not a math practice, in order for us to generate data, we need an investigation. The purpose of engineering investigations might be to find out how to fix or improve the functioning of a technological system, or to compare different solutions to see which is best to solve the problem. We saw this in some of the posts so far. There were posts on creating a system to design a system to best wrap a set of gifts, or we've also seen posts regarding the improving of a hypertufa pod, or maybe improving the design of a pizza. All of those are technological systems. People typically think of technology as being digital, meaning computer related, but that's not the case. Technology is all the things we do to modify the natural world. So if you think about that, the fact that I keep my iced tea in a glass, that's a technological system, because all of those things are modifications of the natural world. Engineers use investigations to gain data essential for specifying design criteria and to test their designs. Like scientists, engineers must control their variables. Once we have our data, we need to analyze it. So engineers make decisions based on the evidence that a given design will work. They rarely rely on trial and error. Often analyze a design by creating a model or prototype and collecting extensive data on how it performs, including under extreme conditions. Now, we're probably not ever going to get to extreme conditions, but what all that means is it's perfectly permissible to give students a basic design and have them analyze that design, then use that information to offer suggestions for design improvement. A lot of what we do in these science classrooms, it's really hard for kids to design a vehicle when they have no idea how a vehicle works. They can't just design things out of thin air. So it's permissible to give them a basic design and then challenge them to make improvements to that design. That is engineering. Analysis of this kind of data not only informs design decisions and enables the prediction or assessment of performance, but helps define or clarify problems, determine economic feasibility, evaluate alternatives, and investigate failures. So keeping those two ideas in mind, I was thinking of what could be a tool that uses math. And beyond the normal, like rulers and protractors and all that, I was thinking about the pantographs. Now, if you're interested in this, notice up here I give the website of where to find the information and the full activity. Science Buddies is a great website resource, and it has a lot of stuff for science fair type projects, but it also has, notice here, an area for STEM activities that you might want to investigate further. So notice we have two different designs, and this is made simply with two short pieces of cardboard and two long pieces of cardboard and 4 brads. So with our short design, or with one design here, we put a pencil on the short arms and the pen on the long arms, and in our second design, we keep the pen on a long arm, and we put the pencil back here in a long arm. So the question becomes, once kids make the design, or once kids build the pantograph, is if I copy the drawing with a pencil, what happens with the marker? And once students do that and look at what happens and maybe make measurements so they can get into the idea of the scale factor, is to ask students how the result might be influenced by changing different pieces, right? What if I change the length of the long arms? What if I change the length of the short arms? Is there a magic between the size and where these are located for each one of these? And what if I had a picture over here and copied it? What would happen here with the pencil? The same questions can be asked when I change my fixed point as well. So by going through these investigations, students should get a fairly clear idea of how these machines work. How does these pantographs work? And once they have those ideas, then you can follow it up by asking them to make a pantograph that scales your drawing by a specific factor. Because right now we don't know what the scaling is, and maybe we can control that, maybe we can't control that. Maybe this design doesn't work to control that, but there's something else that does. So that provides students the opportunity to do several things. First and foremost, take data from their investigation into the pantograph to determine how it works, and then incorporate that data into a new design. And it might be a new design completely or a modification of the first design. Either one of those is permissible, as long as it meets the criteria specified. Now, like I said, this isn't necessarily a problem that I would a problem in the format that I would use to present to students, but this is my process. So I've decided that there's a couple of skills I'm interested in. I'm interested in that students do some sort of investigation of a design and then use that information after analysis to make improvements to the design. And from that, I developed my problem. Now, I usually like my problems to be more authentic. And one of the things that popped in my mind as I was thinking through all this is when I was at Mount Rushmore, I noticed how they made the faces in the mountain. So they used a model of what they wanted the faces to look like, and they took a a protractor with a plumb bob hanging off the end of it, and made measurements, different measurements. They had the same device, but much larger at the top of each of the faces, and they use those measurements with a scale factor of 12 in order to draw on the mountain what they expected to see. So to me, even though they're not using the same device to make a scale drawing, it's still another way to mathematically make a scale drawing. And students, hopefully, by the time they're done working through some of these problems and stuff, will have a better understanding of scale. I hope this helps. If it doesn't help, feel free to contact me through Moodle, and I will be happy to answer your questions. I hope you all have a great week.